So in the previous lecture, we were talking about how to represent signals using step functions. Today we'll begin with an example that was left over from the previous lecture slides. This is representing signals in terms of ramp function. At this time, let's quickly take a look at what a ramp function is, right? Like ramp function is going to be 0 for all times that are less than 0, and then for times greater than 0, it is going to be a signal that linearly increases with a slope of 1. So in this case, your slope is 1. The x-axis is time, and the y-axis is simply r of t. And it keeps going up, right? And this is time 0. So that's how we defined r of t. Now our goal is to represent this arbitrary signal. It is a trapezoid looking waveform with it's going to be 0 for time less than 0. It is linearly increasing with a slope of 1. So let me highlight that with that slope of 1 there. And over here, it is decreasing linearly with a slope of what? -2, because the change in y is 2, while the change in x is from 6 to 7. So just 1. Between the time 2 and 6, it is constant, simply 2 there. So our goal is to represent this f of t using ramp functions or r of t's. So we can have our signal operations going on for this. Like we can shift signals that are in terms of r of t. We can scale them. We can do an amplitude scaling for them. We can do all that kind of stuff. But that's our goal. So we'll start with all the way to the left, right? Below. So when time is less than 0, we have nothing at all. It's 0. So we would not need any r of t over there. In other words, we would not need to shift r of t to the left, meaning advance r of t. We wouldn't need to do that. So our first piece of f of t can simply be a linear function for 2 seconds. And because I'm representing the entire signal in terms of ramp functions, what I'm going to do is I'm going to express only r of t here. So I can have one r of t. Let me draw a straight line there, like that. So this is r of t for time greater than 0. It keeps going up. Now, as you can see, at time 2, I need to cancel out that slope. So I need to make sure that I cancel out something going up with a slope of 1 by subtracting something that is slope of 1. But I need to do that at time 2. So let me draw the second piece in blue here. That was going up. Now this needs to go down. So 1, 2, all right, I can do that. This is going to be what? This is going to be negative r of t minus 2 because I've shifted it to the right by 2 seconds. What I have next is, so after 2, this guy goes up by 1, this guy goes down by 1 slope, so they cancel out. Now what is going to happen at 6? I have a critical point at 6 where if there was a constant, I would need to have a slope going down with -2. So let me use maybe a different color here. Let's say we have green there going down. So this is 3, 4, 5, 6. At 6, I would need to go down here. But this is going to be with a steeper slope. So this is going to be -2 r of t minus 6 shifted to the right, so or delayed by 6 time units, and an amplitude scaling of -2 because the slope is -2. And then at 7, I need to cancel everything out. So I would need a different color here. Let's say at 7, I have going up with a slope of 2 as well. So that at the end would be 2r of t minus 7. So this is 7, and let's see, this is going to be 6 here, all that. So if you add up all these pieces individually, you can see that goes up, cancels out, goes down, cancels out, and you get that overall the same signal. Let me erase this because we don't need this anymore. I can combine all of that and express in terms of an equation. F of t equals, what do I have? R of t plus, minus R of t minus 2 minus 2 R of t minus 6 and plus 2 R of t minus 7. So that's f of t expressed in the form of ramp functions. Now, one hint that I will give you is, in some cases, you might not be able to express f of t in the form of R of t's. So for those some specific cases, if suppose you need u of t, you can represent u of t as simply the time derivative of R of t. This is a hint for problem 1 on the coming homework. So I hope you take advantage of that. Time derivative of ramp function is u of t. Let's talk about the bracket notation for f of t. What is the bracket notation? This is f of t. In this case, I have several pieces. 1, 2, 3, 4, 5 pieces. So let me draw a bigger curly parentheses here. It's going to be 0 for time less than 0. Then I have R of t between 0 and 2. Then I have R of t minus R of t minus 2, that is between 2 and 6. Then I have R of t minus R of t minus 2, and I would also need to do minus 2 R of t minus 6. That's between 6 and 7. Finally, I have the entire thing, R of t minus 2, 2 R of t minus 6, plus 2 R of t minus 7. That is going to be between 7 and 8. Greater than 7. So I can say infinity. All right. We can also color code this. Let's see. This was red. This was, well, it's going to be too long. Let's just leave it like that. Okay, so that's bracket notation. There we have written up our function in this form as well, and we have sketched the individual piece. Let's see, there's a question, gradient. So there's a question about the ramp function slope. Why is this negative? The gradient, so if I have to cancel out something that is increasing with a slope of 1, if I have to cancel that slope out and make it slope 0, then I need something that is going down with a slope of 1. Right? So only then this guy keeps going up, this guy keeps going down, so they cancel each other out, so that between 2 and 6 you get something that is constant. That's why I would need a slope of -1, which is essentially an amplitude scaling here, and shifted by 2 there. So that's why the blue line has a slope of -1. That R is not the slope. That R is essentially the function, ramp function, R of t. Let's see. Another question is, so we can use the ramp function in problem 1, where it asks us to describe the function signal using unit functions. Uh, Jason, this is not yet posted homework. So that homework has not been posted yet. The thing that I'm hinting, yeah, no. I mean homework 4, the one that I'm going to be posting later today. All right. Other questions about this example? So the reason why I'm giving you a hint is because while simply using R of T's, one of the signals that I'm going to show, you cannot represent it if you just simply use R of T's. So you will have to use this particular trick, derivative of R of T. All right, let's keep moving here. Another quick example, now that we have gotten some a little bit comfortable with manipulating the slopes, let's try to take a look at another example here. F of t is given to us. It's a triangle looking waveform. Let's see. All right, f of t, express f of t in terms of ramp functions. So for this, let's see. From 0, it increases linearly with a slope of 1 because at 2 it is 2. And then between 2 and 4, it goes down also with a slope of 1. So to answer this, I would say f of t equals, from 0 to 2, I would need r of t. From 2 to 4, because I need to change the slope by a factor of 2 units, right? I need to change it from +1 to -1. So I need to do a subtract 2 r of t minus 2. And then at 4, I need to cancel one of them out. So plus r of t minus 4. So if I think of it in terms of monitoring the slope of a linear function, over here it is 1. Over here between 2 and 4, it is going to be 1 minus 2, so -1. And then after 4, it is going to be 1 minus 2 plus 1, which is going back to 0. So that's how you would represent f of t in terms of ramp functions. So literally we did 3 pieces to this, right? One piece was right here, the other piece was right here, and the other piece was right there. This was slope of 1, slope of -2, slope of 1 again. All right, let's see. The second, let me copy this because I will need this later on. Copy. And I will paste it over here because I need this as a reference. I have another signal over here called g of t. It is a variation of f of t. Earlier, if you look at f of t, it was a triangle. 0 to 2 it increases, 2 to 4 it decreases, slope of 1 and -1, and height is 2. And g of t is very similar to that, except the amplitude goes up by a factor of 2. So that would simply be 2 times f of t. Well, I'm not going to write t just now because there is also a scaling in the time. So the signal has expanded by a factor of 2. So when the signal expands by a factor of 2, we need to do a time scaling operation as 2 times f of t divided by 2. So in this case, let's see, f of t was represented in terms of r of t. I can represent g of t in terms of f of t as I just did, with an amplitude scaling as well as a time scaling. Then because I have a relationship between f of t and r of t, I can use the previous result to say 2 times f of t divided by 2 is simply going to be 2 times r of t divided by 2 minus 2 r of t divided by 2 minus 2 and plus r of t divided by 2 minus 4. All I'm doing is I'm doing a change of variable from t divided by 2 here, here, and here to get t divided by 2, t divided by 2, t divided by 2. And 2 remains as is, so it's a factor for everything. All right, so I hope these two examples give you a little bit of comfort with ramp functions, how to represent linear functions used in terms of ramp signals. If it's a quadratic, then you would have to have more derivatives that will need to be involved. All right, so let's see. This is done. This is done. We can move on to the next lecture here. So lecture 4. Lecture 4, we are going to focus on discrete time signals first. All right, before that, there is a question about, let's see. So there seems to be some confusion about g of t. Why is that 2 times f of t divided by 2? Well, if you see this, f of t was that 0, 2, 4 with a height of 2. So if you want g of t, that 2 needs to become 4, right? So that means that we are scaling the amplitude. We are making this triangle taller by a factor of 2 because of that to that. So that's why we have that 2. And then this 4 time units is becoming 8 time units. So there is a time expansion by a factor of 2. So that guy is responsible to make that 2 there. And that factor is contributing to the amplitude scaling of 2. So there are two things happening. One is the time scaling and the other is the amplitude scaling. All right, let's go back to lecture 4 here. We are going to be focusing on discrete time signals first. So discrete time signals look like the plot that is shown on the right. In terms of your time, they are discrete. So only selected values of the continuous time signal are being used to represent the function. On the left, we have a continuous time signal. So let me write that down. Over here, this is a continuous time signal. CT, continuous time signal. F of t, the x-axis is time. T is the continuous time variable. Now, if I were to sample this f of t for every cap t seconds, I would get f of small n, where n now is the discrete time variable. N is the discrete time variable, which is specifically the integer sample index. So it goes from 0, so plus or minus 1, plus or minus 2, 0 is also included, so on, right? It increases in both directions. It's going to be an integer sample index. So let me mark those values here. 0, 1, 2, 3, and so on. This is -1, -2, -3, and so on. So that's your x-axis n. That's the discrete time variable. Now, how do I go from f of t to f of n? In terms of convention, note that n has a square bracket around it, t has a parenthesis around it. So that's a convention for continuous time and discrete time signals. Now, f of n is essentially evaluated as f of small n cap t. So n is going from 0, 1, 2, 3, and so on, also -1, -2, -3, and so on. And we are essentially evaluating the function at those specific times, nt. So 1t, 2t, 3t, and so on. And the way we are getting this if you look at this, if I move this over, that exactly matches up. So I have essentially sampled the signal to get a set of samples, a sequence of numbers. That's my discrete time signal f of n. Evaluate the continuous time signal at discrete integer multiples of the sampling time. In this case, the sampling time is t. So we are evaluating the function at 1t, 2t, 3t, so on. Also f of 0, f of minus 1t, f of minus 2t, and so on. So the values of f of t at t equals 0, plus or minus 1t, plus or minus 2t, and so on. So that's how we are going to go from a continuous time signal to something that is discrete. So we only need to store, process, manipulate limited number of values in the signal, as opposed to doing that for every value in the signal. Now, let's, in terms of continuous versus discrete, a lot of things are going to be very similar. It's just that, some operators might change, but in terms of their general properties, a lot of things are going to be very similar. So let's take an example here for the step sequence. U of t is a unit step function. On the top, we have the continuous time representation. So it's 0 for time less than 0. And as soon as t goes above 0, indicated as cap t, cap 2t, 2 cap t, 3t, 4t, and so on, it is becoming a 1. On the right column, we have its representation in the bracket notation. So for time greater than 0, the unit step or the step signal is 1. And when the time is less than 0, it is 0. So if both of these combined, you got 1 there and a 0 there. Now, if I pick out the samples evaluated at t, 2t, 3t, and so on, and negative t, negative 2t, and so on, I will get a sequence of numbers. What are those numbers? 0, 0, 0, 0, so for all the times that are negative, you get a 0. And for all the times including 0 that are positive and greater than or equal to 0, you get a 1. So that's your unit step sequence. In discrete time, Will, you're absolutely right. U of 0 is part of the step. So it's being considered as already the jump has happened to 1 when you sample it. So 1 is part of n greater than or equal to 0. Let's see. Now, over here, we are representing things in the form of a bracket notation for u of t and also for u of n. There is another form of representing the discrete time signals, which is using the fact that it is simply a sequence of numbers. So if it is simply a sequence of numbers, I should be able to represent u of n as a sequence of numbers using curly braces. So I got several zeros, and I've got a few zeros here. Then I've got a bunch of ones that will continue, right? So I've got all zeros here, then I've got all ones here. Now, an obvious question over here is, if I were to represent this, which is the same as this, I should have some way to indicate where that n equals 0 is. And the way you indicate n equals 0 is by simply putting an underscore at the number which corresponds to n equals 0. So let me highlight that. Underscore indicates n equals 0. So things that are to the right are going to be 1, 2, 3, and so on, increasing values of increasing integers of n, and to the left are going to be for decreasing integers of n, negative 1, negative 2, and so on. The underscore is what indicates n equals 0. So if you were asked to sketch this from the sequence of numbers notation, we can quickly do that. That's your step sequence. Now let's talk about the Kronecker delta function, also called as the unit impulse. We need to sample delta of t. Delta of t is our impulse function or the delta function, which is the area or the weight is 1, and that happens only when time equals 0. At all the other times, you have nothing. So essentially you have this, right? Delta of t is only valid. And its height is infinity, but the area under that is going to be 1. So its weight is 1 at that time. So when we sample it, we need some way to represent the Kronecker delta. Delta of n. For n other than 0, you have a 0. And when n is 0, you have a 1. So over here, the weight was represented as 1. Over here, it is being translated into the amplitude of that particular sample, 1. How can I represent it in the form of sequence of numbers? Let's do that here. Delta of n is a bunch of zeros, and I have a 1 at some place, and then I have a bunch of zeros again. And I need to put an underscore when n is 0, which is for the sample value 1. So that's our unit impulse. Let's do an example here. We are given some arbitrary sequence of numbers defined as x of n. Actually, we are missing something, right? We don't know where the 0 is. So let's put that underscore under the 1. And we are asked to express this as x of n using unit impulses or the Kronecker delta functions, delta of n's. So how can I do that? Well, let's do this individually. I need a 1 there at n equals 0, and I need a -2 when n equals 1, and I need a +3 when n equals 0, 1, 2. So let's see. For that first one, what would I have? I would have a delta of n. I should say 1 delta of n. And for that -2, I have 2 delta of n minus 1, move to the right by 1. And I have plus 3 delta of n minus 2. So let me color code them. That's going to be the pink one. This is going to be the blue one. And finally, this is going to be the yellow one. And the way they look, I've got, let's see, zeros everywhere. Let me move this a little bit so that we can see clearly. Then we go into at 0, I have a 1. At 0, I have a 1, -2. Then I have 3 on the other side. Everything else is 0. I think you get the idea now. Let's see. And black. All right. So we have sketched it, we have put out all the samples, everything else is 0 for other times. This is time 0, this is time 1, this is time 2, this is -1, -2, 3, and so on. All right, so I hope that was helpful, and I hope you also see that there is going to be you can generalize this. You go as far to say that you can represent any discrete time signal using unit impulses. All you have to know is what are their values at those discrete time intervals, 1t, 2t, 3t, and so on, and -1t, -2t, and so on. So it turns out that this Kronecker delta function is very, very crucial. Hence, our next slide. Represent step sequence using unit impulses, or the Kronecker delta functions, delta of n's. How can I represent this u of n using delta of n's? Well, all I need to do is add delta of n plus 1 delta of n minus 1 plus 1 delta of n minus 2 and so on. So I keep shifting delta of n right by 1, and all I have to do is add everything up. So u of n can be simply written as a sum of all the boxes that are shaded here. Delta of n, which is the unit impulse, delta of n minus 1, unit impulse shifted to the right by 1, delta of n minus 2, unit impulse shifted to the right by 2, and so on. It keeps going because this keeps going. Let me also show that here clearly. This keeps going. So the summation will keep going. Now, in terms of in closed form, you can write that summation as u of n is equal to delta of n plus delta of n minus 1 plus delta of n minus 2, and so on. That sum keeps going. All of this can be represented as a summation using the sum property of the unit impulses. So u of n is simply delta of n minus k, summation of delta of n minus k, where k is going from 0 to infinity. So you get delta of n minus 1, delta of n minus 2, and so on up to infinity. That is going to give you your unit step back. So that's the sum property of unit impulses. Now let's see how we can deal with this in a more generic sense. Like I said, this unit impulse Kronecker delta function is going to be very crucial for sampling any arbitrary discrete continuous time signal. So all we have to do is sample the signal, continuous time signal. We get a set of samples as shown over here. This is our continuous time signal f of t. Then we sample it, and we are representing on n here. You see, first you get samples, right, for nt, 1t, 2t, 3t, and so on, where t, cap T, is the time difference between those any two samples. Then we have taken those samples and expressed it in the form of an index n. So 1 actually corresponds to what is the value of f of t at 1t, where cap T is the sampling time. So, in other words, if I took this and I mapped it onto that would exactly line up on top of each other. So sample first. Once I have those samples, what are they? Those are f of 0, f of 1, f of 2, f of 3, and so on. So if I were to represent f of n as a summation of scaled unit impulses, I should also say scaled and shifted unit impulses, all I would have to do is represent each one of those samples as f of n multiplied by delta of n plus 3, which is delta of n plus 3 is right there. And if I scale that unit impulse by f of n, whatever that value is, corresponds to that, I will get that particular sample. And similarly, I do that for f of n multiplied by delta of n plus 2, delta of n plus 1, and this keeps moving to the right to get all of those samples. And when I add it up, I get my entire signal back, which means I can represent f of n, any discrete time signal, as a summation of weighted and shifted unit impulses. Those weights corresponding to f of minus 2, f of minus 3, f of 1, f of 2, f of 0 also So those are the amplitudes of each of those samples, and they are shifted because you need at each integer time interval. N is 1, 2, 3, and so on, 0, -1, -2, and so on. Now, once we have this product, we can express this as a summation. But also note that there is a product property that we have that is at play. Where is this product property coming from? This is product property is coming essentially from the discrete version of the product property of the impulse function, which was dealt in continuous time earlier on. So if I go back to my lecture here and I point that out to you, let's see, this was in the previous lecture right there. X of t multiplied by an impulse at t0 is evaluate x of t at t0 multiplied by delta of t minus t0. All we did is replace the t's with the n's and t0 with some n0. That's it, to get our discrete version of that product property, which is right here. So when you multiply a discrete sequence with an impulse present at some arbitrary time n0, you get an impulse present at that arbitrary time n0, which has now scaled by f of n0. So that its amplitude has changed based on the value of, so evaluate the function at n0 and that becomes your new scaling. Why is k negative infinity? Because the signal can be going from negative infinity to infinity. In the previous example, we had unit step, where in unit step, we were only accumulating values that were 0 or greater than 0. For any arbitrary f of x or f of t, we can have values that are less than 0 all the way to negative infinity. We can also have values that are greater than 0 all the way to plus infinity. So we need to incorporate all those times where, so k is going to go in the general case from negative infinity all the way to plus infinity, because we have a sample in the negative times as well as in the positive times. This is the more general case. So let's try to just look at one term here. Delta of n plus 2. Where is that? It is right here. Right. But do we agree with this? Well, for this, using the property, what would we write for that? We would have to, oh, sorry, too big. We would have to evaluate f at negative 2 and then multiply it with delta of n plus 2. And that is exactly what we are writing over here. Similarly, we do that for all the samples from negative infinity to infinity. So there is a continuation here of terms, there is a continuation here of terms. And all of that can be expressed as a summation using a summation sign where k goes from negative infinity to infinity, f of k delta of n minus k. Scaled and shifted unit impulses can be used to represent any arbitrary discrete time signal. I hope that is helpful. So, you know, when we go into the topic of sampling and signal reconstruction, we will we will revisit these topics. You know, essentially we'll go into sampling time. Are there any limitations on this? Can we have the sampling time really small or really big? What are the consequences on that? What are the limitations on that, and so on? All right, let's move on here. Let's talk about the ramp sequence. Ramp sequence, similar to the unit step sequence, is 0 for time less than 0. And it is going to be 1 for 1, 2 for 2, and so on. So it is 0 for all the time that is 0 and negative. It is going to be 1, 2, 3, 4, and so on for times 1, 2, 3, 4, linearly increasing as time increases. So that's your R of n, the ramp sequence. Can I express this in the form of a sequence of numbers? Quickly, R of n can be represented as, in curly parentheses, bunch of zeros, and after that it becomes 1, 2, 3, 4, and so on. And the 0 is right here. N is 0 there. All right. Now, using what we have learned about unit step sequence, unit impulse, and the ramp sequence, we can talk about 5 different relationships between those 3 things. So these are summarized on this slide, and as we go on in this lecture, we will be proving some of them, looking at a little bit deeper into some of them as well. The last sampling property, that is, we are not going to go deeper there because we have already talked about the sampling property for the continuous time signal. So we are essentially looking at the discrete version of that. So we have dealt with 5. We'll be looking at the other 4. As you can see, all of these relationships rely on 3 things: unit impulse, step sequence, and the ramp sequence: delta of n, u of n, and r of n. Let's take a look at the first one, which is the sum property, which is, can I represent u of n as a summation of shifted unit impulses? We looked at the sum property earlier on. Let's take a look at its corresponding first difference. So we have taken a look at first one earlier. Let's take a look at the second property here. First difference of the unit step function, delta of n, can be represented as u of n minus u of n minus 1. Is that true? Let's validate that statement using this particular sketch. On the left, we need to sketch u of n. On the right, we need to sketch u of n minus 1. So let me do this in red. Over here, I've got a bunch of zeros. Let's see, 0. Okay, so if I separate them out in terms of 1, that's fine. And then I have 1, 1, 1, 1, 1, and so on. And it keeps going. That's u of n. Now, u of n minus 1 is going to move over to the right by 1. And everything else is going to be 0, red. Now, when I subtract them, what do I get? For time less than 0, everything is 0. So that's not a problem. I can just put a 0 there. For time that is 1 and greater, 1, 2, 3, and so on, I have 1 minus 1, 1 minus 1, 1 minus 1. So that is also 0. But at 0, I have 1 minus 0, which is 1. Which indicates that I have delta of n there. So that's called the first difference of the unit step function. Now, a quick example here. What is delta of n minus 2 going to be? Well, can I represent delta of n minus 2 in the form of unit steps? Instead of n, I now have n minus 2. So this would be u of n minus 2 minus u of n minus 2 minus 1, so n minus 3. So we are essentially just doing n minus 2. So do that over there, there, and there. So we are simply changing n to n minus 2 to get that new identity. So everything gets shifted to the right by 2 time units. All right, so I hope that you found that helpful. Next, a running sum. Can I represent r of n as a summation of shifted step sequence? So let's take a look at that. The running sum on the next slide. To do this, let us evaluate r of -1 first. What is r of -1 based on this property? R of -1 is simply summation m equals -infinity. Instead of n, I would have -1 u of m minus 1. What would that evaluate to? As I sum m from -infinity to -1, I have u of -infinity plus u of -infinity plus 1 plus and so on, plus what? U of -3 plus u of -2. And that's it. I need to stop there. Because the lowest I can go or the highest I can go is -1. -1 is -2. That's it. What are each of these terms? Let's do that in black. U of -infinity is 0. U of -infinity plus 1 is 0. All of these are 0. U of -3 is also 0. U of -2 is also 0. So this is 0, r of -1. And let's do a next one, r of 0. You have summation m equals -infinity to 0 u of m minus 1. In this case, the highest value of m is going to be 0, which means the highest contribution from the unit step sequence is going to be u of -1, which is still 0. So 0 here. How about r of 1? Summation m equals -infinity to infinity u of m minus, not infinity, sorry, 1, u of m minus 1. What is that? U of 0. So this can be actually written as r of 0, the previous sum, plus u of 0. So we are writing this as that plus a new term, because all we did was increment what by the upper limit by 1. And now this was 0, and then this equals 1. So we can say this equals 1. Similarly, if you did that for the rest, you get r of 1 plus u of 1, which is going to be 1 plus 1, 2. And then I hope you see that r of n, this is exactly what we have for the ramp sequence. It is 0 for time less than 0. It is going to be 1, 2, 3, and so on for times n equals 0, 1, 2, 3, and so on. So that's exactly what you have for r of n. So this is a quick proof that you can represent r of n as an accumulation of unit step sequence from -infinity to some stopping value n, and that becomes actually your r of n. So this is like integrating in terms of continuous functions. This is like integrating a constant. When you integrate a constant with respect to time, you get t. So that's how you can think of it in terms of a continuous time signal. Let's so there's a question which is u of 0 is 1. So for when you talk about continuous time signals, not in a very strict sense. Let's see, where is what? Yeah, when you talk about step signals, unit step signal, not in a mathematically strict sense, then you actually include an equal to here. However, because there is a when you move on to a very strict conversation where you are paying attention to discontinuities, then you no longer put that equal to sign, and you say greater than 1 it is 1, greater than 0 it is 1, less than 0 it is 0. However, when you sample things, there are only discrete times for which you are observing the signal. It's not like you have some delta t where you are observing that discontinuity. So in this case, think of it as a region around 0 time. And as that region collapses down to 0, as that region collapses to 0, it becomes an impulse at that particular point. So in the limiting case, I will use this as greater than or equal to 0. Let's move on here. Ramp sequence. We did this, this. We also did this. Let's do the first difference of the ramp function. So r of n plus 1 minus r of n, the claim is that it is the same as u of n. Let's try to quickly look at that. We have two signals that we are interested in sketching. One is r of n plus 1. So r of n plus 1 corresponds to r of n getting advanced by 1. So it should move to the left by 1. So this will be 1, that will be 2, that will be 3, and so on. This will be 0, and this will be 0, 2. Let's see, straight line. This is 0, 1, 2, and so on. And then black, I've got -1, -2, and so on. And then the height 1, 2, 3. And on the right side, I have r of n. R of n is simply going to be the same thing, but 0 here, 1 there, 2 there, 3 there, and so on. And then 0 there, 0 there, and so on. Mark the times, mark the amplitudes. Now, if you subtract one over the other, time-wise subtraction. So for each time step you subtract, what do you get? For time less than 0, you have all zeros. So let's quickly sketch that out. 0, 0, 0, and so on. And at time 0, what do you have? 1 minus 0. So that's 1. And then 2 minus 1. Also 1, also 1, also 1, and so on. Height 1 times 0, 1, 2, 3, and so on, which is the same as u of n. So that's a quick proof that the first difference, r of n plus 1 and minus r of n, of the ramp function leads to a step sequence. All right, questions about these 5 properties. Do I have it? That's it. So let's see. Right here, we have also done this. So that completes our conversation about signal classification and signal operations. Now we look into systems. All right, let's get into it. All right. So when we move on to our conversation on systems, we have been on the outside of the system. So for now, we said, okay, there could be an input to our system, and then it'll go through our system with some system operator tau or cap t, and then we get our output signal y of t, which is the system operator cap t applied onto x of t. So the output signal y of t can be obtained by applying that system operator. System in the middle, input on the left, output on the right. Input is also called as excitation, output also called as the response of the system. Some examples of the system you can say, all right, for all of them, let's put some x of t. Note over here, we are talking about continuous time signals, continuous time systems, right? So all these systems are operating on continuous time inputs and outputs. We could also have discrete inputs and outputs as well. So I have put x of t's and y of t's for all these 4 examples. Now let's take a look at some examples there. Let's say our first system is a delay system. So delay by some t0, constant delay t0. So how would I be able to write y of t in terms of x of t? X of t gets delayed by t0. Next example, this could be an accumulator or an integrator. So y of t can be written as an integration of the input x of t dt. Just examples over here. The third system could be an amplifier of some gain g. Y of t in this case can be written as g times x of t. And if you can have an integration, then you can obviously have a derivative. Y of t over here can be represented as dx of t divided by dt. So these are some examples of systems. Now we will know more about the systems if we look at some underlying properties of those systems. And those properties could be linearity, it could be stability, it could be causality, it could be time invariance. There are lots of system properties that we are going to go through next. The first one and the most crucial one is linearity. Is the system linear? That's the question one. Because for almost all the things that are in this course, we will have to consider that the system that we are looking at is a linear system. So we will need to be able to check whether the system is linear or not. And we can check that if we have an explicit relationship between the output and the input for that particular system. Now, in order to check for linearity, there are two particular checks. One is for homogeneity and the other is for additivity. Both combined, you can say the system is linear. So first we'll look at homogeneity. System properties, the first one, homogeneous or not, or the check for homogeneity. The system the system is called homogeneous, or homogeneity is satisfied for any signal x of t and any scalar a. So this is a scalar a. When the amplitude scaling before the system, if that equals amplitude scaling after the system, then the system is considered homogeneous. In other words, if you apply the system operator after you scale the input, and if that is the same as applying the system operator on the input first and then scaling the output by a, then if it is satisfied, you can consider that to be a homogeneous system. So let's take a look at this the consequence of these statements in the form of a block diagram. On the left, I have amplitude scaling before the system. So if this is my system, later, second here and first here, I am doing amplitude scaling before, multiplied by a before, and multiplied by a after. A is a scalar. X of t is the input. Y of t is the output here. If it is the same as go x of t apply the system operator, scale it, then you get y of t. If the output here is the same as the output here, then you can consider that system to be homogeneous. Let's take a look at two examples on this slide where we try to check whether the system is homogeneous or not. Here, this is a convention that I hope that you get that you get used to very quickly. X of t on the right, on the left, an arrow indicating the system. On top of the arrow, you have the system operator t represented. On the right, you have y of t, which is the output of the system. Output is related to the input as a square. So y of t is x squared of t. It is taking the input, squaring it, and you get the output. And the question is the system homogeneous? So we need to do the check. So let's do this in red. So let's assume that x1 of t, I'm defining a new input as a x of t. Actually, let's first assume that this is okay. Let's assume if x of t goes into the system and you get y of t as x squared of t. If that is true, then if you consider a new input signal x1, which is the scaled version, amplitude scaling by a, what would happen if that goes through the system? Same system. You get its corresponding output as y1. Now, how can I write y1 of t? I can write y1 of t as the input squared, which is a squared x squared of t. And as you can see, this is simply a squared y of t. And more importantly, it is not equal to a y of t. So you can say it is not homogeneous. So homogeneity is not satisfied here. Let's do another example. Let's start the same way. If x of t goes into a system with a system operator t, you get y of t. In this case, we have 4x of t minus 6. A new input x1 of t, which is x1 of t defined as some scalar times x of t, goes into the same system. You get y1 of t, which is going to be what? Let's see, 4a x of t minus 6. Actually, write it down in two steps for clarity. Y1 of t is going to be what? 4x1 of t minus 6, which is going to be equal to 4a x of t minus 6. And as you can see, this is not equal to 4a x1 of t, x of t minus 6a. So again, the answer is going to be no. Start off with x of t, scale it first, go through the system. Is it the same as when if you did the system first and then the scaling? If you did the system first and then the scaling, a would be multiplied to both of them. And in this case, it is not equal. In this case also, it is not equal. So both these systems on the slide are not homogeneous. So they fail linearity. They are also not linear. Coming to the second property that we need to check in order for the system to be linear. It has to be homogeneous. It also has to be additive. Additivity over here, the condition is if you sum the two signals that are considered as inputs to a system first and then apply the system operator, is it equal to applying the system operator on the two inputs individually and then summing up their individual outputs? If it is, then the system is additive. If not, then the system is not additive and also not linear. So in terms of a block diagram, let's try to quickly represent this. I'm going to say this is summing before the system. So let's assume that there is a sum here and there is a system here. There's an output there and there is an input there and an input there. They are both getting added here. And similarly, I have two systems here followed by the summer and the output there. What else? Inputs. And now we can draw things up. So over here we have x1 of t, some input, another input x2 of t, going into the sum, then going into the system operator to get y of t. Now if that equals, that's the check, if that equals the next one, which is x1 of t, x2 of t, do the system operator first, then do the summer to get y of t. If both the outputs on the left and they're on the right, that is summing before the system and summing after the system, if they are the same, then the system is considered to be additive. Now let's try to answer this question. Is this system additive? 4x minus 6. So take the input, multiply it by 4, subtract 6, and that's how you, get the output. Is this system additive? So for this, we will have to go through a similar sort of check that we did for homogeneity. So let me lay out the steps here. We assume x1 of t goes into the system operator to get y1 of t, which is 4x1 of t minus 6. Similarly, another input x2 of t goes into the system with an operator t to get y2 of t, which is what? 4x2 of t minus 6. Then we define, let x3 of t be the sum of x1 of t and x2 of t. If that goes into the same system operator, you get y3 of t, which is 4x3 of t minus 6. Now x3, I know it is 4, x3 is what? x1 of t plus x2 of t minus 6, which is 4x1 of t plus 4x2 of t minus 6. Now, if we did the other way, which is system operator first and then the sum, we would literally have 4x1 plus 4x2 minus 12. So the important step here is to note that this is not equal to 4x1 of t, or let me do it this way. It's not equal to y1 of t plus y2 of t, which is in this case 4x1 of t plus 4x2 of t minus 12, which is why we say it is not satisfying the additive property. I hope that was helpful. Next, let us put all of these things together, meaning let us define linearity. A system is considered linear if it holds both the properties that we just discussed. So it has to obey homogeneity. It also has to obey additivity. If one of them fails, then it is not linear. So how can I combine the two properties that I've laid out in homogeneous and additive into a check? So how do I check for linearity? How do I combine both of these properties? So let's do that. Let's define how you check for linearity here. So I start off with x1 of t. I go through my system operator to get y1 of t. And then if I know the system, I know what y1 of t is. Then I consider another input x2 of t. I go through the same system operator to find y2 of t. And because I know the system operator, I can find even that, y2 of t. I can express y2 and y1 in terms of x2 and x1. Then I define a new signal, x3 of t, which is some scalar a multiplied by x1 of t, that is taking care of the homogeneous property, plus b x2 of t. A and b are scalars, and you are combining the check for homogeneity and the additivity in this. Goes through the system operator, and if it is equal, say the output is y3, and what you're checking for is it equal to a y1 of t, same scalar a and b, plus b y2 of t. If it is equal, then it is linear. If it is not equal, then it is not linear. So I hope you can see that you have combined both the properties over here by writing the a and b scalars and also adding them up. So one check for both properties with linear. Let's check whether this system is linear. I have x of t minus x of t minus 1. My goal is to check whether the system is linear or not. So quickly run through the similar sort of steps. x1 of t, input, system operator, I get my output, y1 of t, which is x1 of t minus x1 of t minus 1. Signal minus the delayed version of the signal. Next, yeah, they can be real or complex scalars, but they have to be scalars. Let's see, x2 of t, system operator, y2 of t. What is that going to be? x2 of t minus x2 of t minus 1. Next, let's define x3 of t, which is a x1 of t plus b x2 of t. Go into the system operator to get y3 of t. Now y3 of t I can write as x3 minus x3 of t minus 1. X3 of t is a x1 of t minus plus b x2 of t. What is x3 of t minus 1? It is minus a x1 of t minus 1 minus b x2 of t minus 1. Next, let's combine. I've got a for x1 of t minus x1 of t minus 1, and then plus b, let's see, x2 x2 of t minus x2 of t minus 1. And if I look at this term here, sorry, that looks exactly the same as y1, and this term over here looks exactly the same as y2 over there. So I should be able to write a times y1 plus b times y2 of t. So it is linear. I hope that was a helpful check. Let us do it for a discrete time system. So over here, instead of y of t's and x of t's, you have discrete time signals. X of n is the input, y of n is the output of that discrete time system, and the output is computed for every n as x of n multiplied by 2 raised to n. So x1 of n, same steps, system operator, you get y1 of n, which is equal to x1 of n multiplied by 2 raised to n. Next, we have x2 of n, system operator, y2 of n, x2 of n, 2 raised to n. Next, we have x3 of n, let x3 of n ax1 plus bx2 go into the system, find the output is going to be y3 of n, which equals x3 of n 2 raised to n. So for the output here, I say this equals, instead of x3, I'm going to write ax1 plus bx2 2 raised to n, which is going to equal, let's see, a x1 of n 2 raised to n plus b x2 of n 2 raised to n, and I think this should be okay. X1 of n 2 raised to n is right there, and x2 of n is right there. So I should be able to say a y1 of n plus b y2 of n. So this is also linear. All right, questions so far. How to check for homogeneity, how to check for additivity, how to check for both combined in terms of linearity. Now, apart from systems being linear, they also have to be time invariant. What does time invariant mean? Time invariance, or TI, this is a way to classify the system. We have classified the system as linear and not linear. Now the next system classification is whether the system is time variant and time invariant. So you will hear this term used a lot, LTI systems. A lot of the things that we will work on during this class, the systems that we will consider will obey, or you will have to assume that they obey LTI properties, which means those kind of systems are linear and also time invariant, which means the properties of that system do not change with time. The property of that system is the same today, the same tomorrow, the same day after, right? So if it's differentiating today, it'll differentiate tomorrow, it'll differentiate day after as well. So the properties of that system, the system operator, doesn't change with time. So if you combine linearity and the time invariance, you get LTI systems that you see a lot. In fact, one of the really important topics of this course is superposition. And if you have taken a circuits class, you might have heard the concept of superposition being used when you have multiple inputs, multiple sources. In order to be able to apply superposition, the system needs to be linear and time invariant, LTI systems. So we looked at the first piece of LTI, the L, the linearity. Next we look at the time invariance, the Ti property. So let's define it first. A system is considered a system is considered time invariant, Ti, if the time shifting of the input signal results in the same time shifting of the output signal. So if I shift the input by tau, or in this case t0, the output also gets shifted by exactly the same amount in the same direction. So if it is getting delayed by t0, the output also gets delayed by t0. If it is getting advanced by t1, the output will also get advanced by t1. If that property holds good, then we can consider that system to be time invariant. So formally, how would we write it? If x of t is an input to a system with system operator cap t, y of t is the output, then if you shift the input by t0, the output also gets shifted by the same amount for any input x of t and for shift t0. In this case, t0 can be positive, can be negative. If it is positive, that corresponds to a delay. If it is negative, that corresponds to an advance of the signal. Now, we can represent time invariance using block diagrams like this. Let's write down the inputs and the outputs before and after. Let's see, x of t is the input here, y of t is my output there, and also here x of t there and y of t there. So let's consider time shift first. Let's say by t0. So if you do a time shift first and then you go through the system operator, it should be the same as going through the system operator and then doing the time shift by the same amount. So if the outputs in both these cases are the same, then the system is considered time invariant. We can capture that block diagram into a statement, which is time shift before or after the system is the same. If it is, then it is time invariant system. We talked about LTI system and how the concept of a very powerful concept of superposition is going to be applicable only for LTI systems. Let's take a look at its corresponding discrete time equivalent for time invariance. Very similar. Instead of x of t's and y of t's, you have x of n and y of n. So discrete time input, discrete time output. In the middle, you have that system operator cap t. If that is the input output combination for a discrete time system, then if you shift the input by n0, you also have the same shift for the output y of n. So y of n minus n0. So for that holds for any input x of n and for any integer shift n0. In this case, the n's are all integers, so the shift also has to be integer. So let's do a quick check here for a discrete time system. We are asked to see y of n equals x of n multiplied by 2 raised to n. Is it time invariant or not? So let's start with x of n. Go into the system, find y of n. x of n and y of n are given. That is satisfied. Then let's consider x1 of n, which is the time shifted version of x of n by n0, integer time. If that goes into the system, what do you have? Same system. y1 of n. y1 of n is x1 of n multiplied by 2 raised to n, which is the same as x of n minus n0 multiplied by 2 raised to n. Now, this is not equal to x of n minus n0 multiplied by 2 raised to n minus n0, which was, this is y of n minus n0. And the fact that it is not equal, we can say system is not time invariant. That means it changes with time. So LTI property doesn't hold, and superposition cannot be applied for such systems. Let's take another example here. In this case, we have an integration. Y of t is integration from negative infinity to some arbitrary stopping time t, x of tau d tau. The question is it time invariant or not? Let's do the same kind of check. Steps are going to remain more or less the same. X of t go into the system y of t, where y of t is integration negative infinity to t x of tau d tau. Note that this t corresponds to that t. Next, we have x1 of t going, which is equal to the delayed version of x, goes into the system with operator cap t. Output is y1 of t, which is represented as an integration from negative infinity to t of x1 of tau d tau. This can be written as integration negative infinity to t x of x1 is what? T minus t0. So this should be tau minus t0 d tau. Now, one thing that could lead to confusion is, why is that tau? So you see, x1 of tau is what? Come on. If x1 of t is x of t minus t0, then x1 of tau should be written as x of tau minus t0, which is what we have done over here. So I hope that you guys see that change. Then let's see, we would have to apply a change of variable here. So because we are integrating with respect to tau and we need our answer as a function of time, what we'll do is we'll do a change of variable. Change of variable to work out the integration. Let's say we have a v which is defined as tau minus t0, and if you differentiate v, you get d tau, and for the limits, your tau limits are going from negative infinity to cap t. Because that, so here, the question online is, why isn't the top limit of integral shifted by t0? Whatever you have over here is there. And because you are not changing the output, that is going to remain the same. Your stopping value is going to remain the same. Next, we have dv, we did change that. So let's take a look at the limits. When tau equals negative infinity, our v is going to be negative infinity because v is tau minus t0. And when tau equals t, for the upper limit, we get v to be t minus t0. So our integration now for y1 is going to turn to integration negative infinity to t minus t0. The upper limit has changed to t minus t0. Instead of x of tau minus t0, I'm going to write x of v dv. And this is exactly the same as x of t minus t, y of t minus t0. Because all we have is t minus t0, y, if you shift this, t minus t0, that changes to t minus t0 right there. dvv is the same as tau and tau. So now your shifted by t0 comes into the picture. System is ti, time invariant, because this equals that shifted by tau, y of t shifted by tau, t0. All right, so I hope this was helpful. Let's finish up with this slide. A couple of things that are remaining. Example over here, we have an impulse function, delta of t. When you integrate that impulse function, what do you have? As you're moving from left to right, no area, no area, no area, no area. And then as soon as you go over that impulse, you get a unit step. So 0 here, and then after that, it is a constant 1 because the area is 1 after that. If you move the impulse function to the right by 2, which is delay of 2, and then you integrate, all that happens is that u of t minus 2, that area that you accumulate moves over to the right by 2. So u of t becomes u of t minus 2. So that accumulation shifts right to the by 2. Now, if you combine those two statements, you can say that the integration is time invariant. By the way, the limits over here are minus infinity to t as well as here, right? T is your arbitrary stopping time. So this is an example of a time invariant system too, an integration. We looked at integration numerically in detail, and we looked at one example for that. So both ways you can sort of validate that the system is time invariant. All right, it's 12:05. Let us stop over here and let us pick up with system classifications again on Monday. I wish you guys a good weekend, a relaxing weekend.